So, hello everyone. Now, we will discuss one characteristics of fiber or textile material, which is not that important for most of the fibers, like synthetic fibers and majority of the fibers is not that important, but it is extremely important for cotton. So, the characteristics is it is a maturity. So, it is primarily associated with the cotton fiber testing. For man-made fiber, there is no reason for measuring the maturity, but for even for other natural fiber, we do not measure the maturity, but for cotton fiber it is extremely important. It has many adverse effect if the fiber is immature. Okay. It directly or indirectly affect the characteristics and quality of product. Now, the concept of maturity is essentially confined to cotton and rarely used with other fibers. So, for other natural fibers like jute, linen, we normally do not talk about maturity, and this is the cross section of cotton fiber, and it has got three distinct layers. Outer layer, it is known as the primary wall, which actually gives the total perimeter of the fiber, and after the primary layer it is called the secondary wall, which is the actually consists of majority of bulk in the cross section, and then the lumen, which is hollow in nature. So, this is the unique nature of cotton fiber, where its center, its inside, it is a hollow. Okay. Now, the maturity depends on the thickness of the secondary wall as compared to the thickness of the lumen, and when the fiber grows and it is getting matured. So, that secondary wall thickness increases. It is a very important feature of cotton is that the fibers are hollow in lumen. Okay, that is a important feature here. Now, at different stage, let us see how cotton fiber grows. The secondary wall gradually it is becoming thicker and lumen gets narrower. Initially, the lumen was wider, its lumen depth was wider, but as the secondary wall gets matured, it gets thicker and lumen gradually it is become narrower. The outside diameter of fiber does not change, that is very important. That is the perimeter of fiber, there is a primary wall, it does not change during the whole development. Okay. That it remains almost constant. So, only the change is that this, if it is getting matured, that means the secondary wall gets thicker and the lumen gets smaller. Okay. The outside diameter of the fiber does not change. New cellulose is laid down on inside of the cylinder, that is secondary wall, the new cellulose is laid down. Okay. The secondary wall represent the major part of the fiber thickness compared to the overall fiber thickness. Okay. That is a major part. that actually shows the maturity. which essentially determines the state of maturity. So, if secondary wall growth of secondary wall is not proper, then the fiber will be immature. If the growth is very good, then it will be mature. Now, this is the picture which shows the 3 different types of maturity. So, this one is mature fiber, where secondary wall thickness is very thick and lumen is almost vanished, it is very thin lumen. This is fully matured fiber. And this one is immature fiber, where secondary wall thickness is very small and proper lumen is there. Now, and this one is dead fiber, where secondary wall thickness is very small, it is not there, only lumen is there. Now, these fibers, this immature or dead fiber, they have problem of actually nape formation. These fibers, their flexural rigidity is very small, very low. So, that is why they easily get bent and they get entangled and form the napes. Okay. So, let us see what are the importance of maturity. The optimum degree of maturity of cotton is required. Okay. That if it is not matured, maturity is not there, above which if it is the fully matured. So, optimum maturity is required, but if the fiber is fiber's maturity is more than the required maturity, then the fiber may be too stiff for effective processing. So, it is that is also not required. If it is a highly matured fiber, that is a very thick secondary wall, that will result the thick stiffer fiber and the spinnability will be poor. Spinnability sometime it will be poor, and below maturity, low maturities, below which it is too flabby and lack of resilience. So, that means its resilience means after bending it should come back. Okay. But if it is the maturity, if it is very low, that means if it bends it will not come back. So, it will tend to form the napes. So, over maturity, although it is a problem, but it is not that problem, its problem is less. Okay. For spinning, the over matured fiber present far lesser problem than immature fiber. Only problem with over mature fiber is its a stiffness, that can be handled by applying different level of twist, or we can use for say coarser count or anyway. But handling the immature fiber, it is very difficult. The twist is it can break easily, or it is a nape formation, and it is a proved that most of the nape generation, nape formation for cotton fiber, it is basically due to the immature fiber. So, during yarn processing, the immature fibers form napes, and it is now clear that napes are almost always associated with thin walled and so called dead fibers. So, if we can actually test the nape, if you can take the nape and test the maturity, these are the dead fibers. So, these are the dead fibers. It actually it bends, it rolled very easily during the process, in carding process, in blow-room process, this can get rolled and form napes, and these napes create problem everywhere. These napes we cannot remove most of the, if it goes beyond the carding, these napes cannot be removed. This will remain in the up to the yarn stage, okay, because these are very small napes. Okay. So, importance of maturities, the napiness is a factor in the dyeing and printing of cotton. So, in cotton fabric dyeing and printing, the napiness creates problem. That means, the napes which consist of the immature fiber does not get then dyed, that is absorb dye, because okay, that is because the thin walled fibers tend to dye in lighter shade than mature fiber, because here the dye uptake is less because of the absence of the secondary wall, okay. And that is why it gets lighter shade, and it ultimately the appearance of fabric gets adversely affected. For the same reason, if there is not an even blending of fiber of different maturity, the result can be streaky dyeing and other adverse effect. Okay. So, that blending has to be, if at all there is some immature fiber, the blending has to be proper, otherwise there will be streaky dyeing. So, you can see this is the dyed fabric and the napes are clearly visible, and these napes, they are not actually absorbing dye, they are not, and or dyed in the lighter shade and create problem. And even this uneven dyeing due to immature fiber also, and this we cannot, if we even with other methods like different types of dyeing method, different chemical method, we cannot remove this. Wherever the immature fibers are there, we cannot do anything, it will actually result the uneven dyeing, like white specks napes. These are the napes, okay, and this will be actually visible, it is like white speck. Okay. These are all immature fibers. Now, after knowing the importance of maturity, now we will discuss the various parameters, how to express the maturity. Okay. So, parameters to express the degree of maturity are, one is the degree of thickening, it is expressed in terms of theta. The degree of thickening is that it is the ratio, it is a ratio of the solid cross sectional area of fiber, the actual cross sectional area of fiber. This is the actual cross sectional area of fiber divided by the circle with the same perimeter. So, if we can unfold this one, and make it circular, that cross section and with the actual cross section, the ratio is the degree of thickening. Okay. So, actual cross section to the, so degree of thickening will be less than 1. So, that means, if the fiber is perfectly circular, suppose this is the bean shaped, if it is perfectly circular, then the degree of thickening will be 1. Okay. So, cotton fiber is normally not circular, so degree of thickening we can get. The optimum value of degree of thickening is generally 0.8 to 0.9, that is the highly matured fiber, it is a 0.8 to 0.9. So, because it will form little bit in bean shaped, it will never be circular. However, this method of measurement is not common, because cross section, measurement of cross section and measurement of perimeter, it is very difficult. But nowadays we can measure by using different photoelectric technique, photographic technique. So, that we will discuss. In AFIS technique we can measure directly the degree of thickening, but for other methods we cannot measure, it is not common, but indirectly we can measure the thickness, the degree of thickening by some empirical equation, that we will discuss. So, as we have discussed here, this is the actual fiber of cross sectional area of A. Now, this perimeter, this is the perimeter P here, this perimeter we have converted into circle whose area is A0. Okay. The perimeter P is pi d, here it is a pi d. So, from there we can calculate A0, A0 is the perimeter square divided by 4 pi. Okay. Now, theta is A, this cross sectional area divided by this cross sectional area, that is it is a by p square by 4 pi, ultimately 4 pi a by p square, perimeter square. This is the degree of thickening. So, if we want to get the degree of thickening, we have to measure two parameters. One is the area of cross section of fiber, actual area of cross section of fiber, and the perimeter of fiber. The measurement of both the parameters are very difficult. In normal case we cannot measure, but we will discuss in other methods, some method we can measure this degree of thickening. Next parameter is that maturity ratio. It is expressed in terms of m, where maturity ratio is the nothing but the ratio between the average mass per centimeter of fiber to the standard mass per centimeter of the fiber. So, that for a particular fiber we know the standard for a particular variety, particular cotton fiber, we know the targeted standard mass per unit length, and if we measure the mass per unit length of the fiber, say in micronear or some other method. So, the ratio is known as the maturity ratio. Okay. Next is that maturity count. What is that? It is the difference between the percent of mature fiber to percent of dead fiber. So, there are typically three different types of fibers are there. One is the mature fiber, second one is the dead fiber, another type of fiber which is in between, which is the semi mature fiber. Okay. And in this measurement maturity count, we take two parameters, one is the mature fiber N and dead fiber. Okay. And this maturity count we can use for various calculation, that we will discuss. Now, coming to the methods of measurement, there are different methods of measurements are there. First is caustic soda and microscopic method. We will discuss one by one. Second one is double compression method. Then caustic air method. Here also we use caustic soda, but the technique is little bit different. Fourth one is high volume instrument method. Then in by AFIS method we measure the maturity by degree of thickening, as I have mentioned, that we will discuss. Then image processing method and NI near infrared method. So, these are the methods of measurement of fiber fineness. First, let us discuss caustic soda method and microscope. So, for caustic soda method we need microscope. So, fibers are swollen in dilute caustic soda solution. So, we actually use the dilute caustic soda solution, and matured fibers they will quickly absorb the soda solution and will become cylindrical in shape. More immature one, okay, retain their ribbon like shape. So, immature fiber will not change their shape, they will retain their immature, that is the ribbon like shape. Okay. The apparent thickness of secondary wall is determined. So, from the microscope we can clearly make out, we can clearly see the apparent thickness. Okay. So, if we see this is the lumen and after that if it some when it is this is the lumen, it has become circular. Now, this thickness we can measure, this is the secondary thickness of secondary wall and as compared to the thickness of the lumen, okay, and along with the apparent width of the lumen, that we can measure here under the microscope. It will give clear picture, and the normal fibers are those that have become deconvoluted and rod like, that we can see clearly it has been deconvoluted and rod like, and the date fibers are those whose secondary wall thickness is measured to be less than 1/5 of the apparent lumen thickness. So, that we can measure, because and normal fiber we can clearly make out it will be rod like structure, and there will be many fibers, there will be fibers which are not rod like, but those cannot be termed as the date fibers depending on the thickness of the secondary wall. If the secondary wall thickness is less than the 1/5 of the apparent lumen width, so then we can tell it call it as the date fiber. Now, again there will be another fiber, here this is the width of the lumen, this is the width of the secondary thickness. Okay. So, this is L, this S width of this. Now, this S here, this we cannot tell it is a date fiber, this is not date fiber, this is also not date fiber, because this secondary wall thickness is although less than the thickness of the lumen, but it is not less than 1/5 of the lumen width. But here if you see, this is the actually it is a 1/5 less than 1/5 of the lumen width, that we can directly measure, and from there we can tell the which one is dead or which one is that partially matured. So, fully matured it is a normal fiber N, and this dead fiber we can term it as D. Okay. And as per ISO method, fibers are wet and swollen in 18% of caustic soda. So, that is the standard method, ISO 4912 method, the grouped according to their appearance. Okay. So, there are 3 fibers that we are grouping: date fiber, normal fiber and thin walled fiber, okay, which is date fiber, normal fiber and thin walled. Thin walled fibers are in between dead and normal fiber. Okay. So, then after knowing after dividing this 3 into 3 parts, we can calculate the maturity ratio. What is that maturity ratio? This is maturity ratio is expressed in terms of M, which is calculated by N minus D divided by 200 plus 0.7, that is the maturity ratio, and this formula is typically maturity ratio is the it is a N minus D divided by 200 plus 0.7, and the question comes how this 0.7 has come. Now, it has been observed experimentally based on large number of data, large number of reading, the most of the fibers, most of the normal fibers the quantity is that if you test 100 fibers, the normal fibers, if we see normal fibers, it is typically it is a 67 normal fibers, okay, and date fiber 7, and in between fibers that other fibers will be that 100 minus 674, it will be say 26. If this is the combination, the fibers are said to be normal fibers, and the data, this equation is set, this is the empirical equation. This empirical equation is set in that in such a fashion that for this type of ratio 67, 7 and 26, because for normal fiber which is producing normal yarn, most of the cases they have found that this is the typical value, this is the percent, okay. For 100% this is 67, 7 and this N and D they are also in percent. Now, try to see if we put this value here, if we replace this value, so 67 minus 7 by 200 plus 0.7. So, it will become 0.3, 60 by 200, it will become 0.3 plus 0.7. So, it will 1. So, maturity ratio of this combination has become 1. Okay. So, that is why the 7, this value 7 comes, it is arbitrary, it is not that there is no logic, there is no scientific logic, but as most of the fibers, normal fibers, it has been observed with that proportion. So, that is why it has come, M becomes maturity ratio becomes 1. Okay. Here, so it is, so where N and D are percentage of normal and date fibers respectively, and one get normally confused here that N and D, people always try to get confused with the N is the actual number of fibers, it is not the actual number of fibers, it is a percentage fibers, percentage of N, and suppose we test say 150 fibers or 1000 fibers, N we have to convert it to in terms of percent, okay, percent N and D. So, a cotton with M less than 0.8 would be regarded as immature cotton, okay, and so N minus D. Now, can we calculate what will be the maximum value of M maturity ratio? Maximum value of maturity ratio theoretically it is when all the fibers are mature, 100% fibers are mature, that means N will be 100, then what will be the D value? D will be 0. Okay. So, D is 0. So, what is the value then? It is a 100 divided by 200, it will be 0.5. So, 0.5 plus 0.7, it is a 1.2. Okay. That means, when all the fibers are mature, 100% mature fiber, in that case maturity ratio will be 1.2. Now, in the extreme case, all theoretically say all the fibers are immature, date fibers, 100% date fibers, in that case N will be 0, D will be 100. So, this portion will be minus 0.5. So, minus 0.5 plus 0.7, that will be 0.2. That means, the range of maturity ratio is from 0.2 to 1.2. Okay. So, that is the range. So, theoretical range of M is from 0.2 for 100% dead fiber, that is D equal to 100, to 1.2, that is 100% mature fiber where N is 100. Okay. And the empirical relationship. So, if we know this calculation of maturity ratio is very simple, using the microscopic technique, using the caustic soda technique, we can calculate measure the maturity ratio, and from there using the empirical relationship we can calculate the maturity, that is the degree of thickening. Okay. This is based on large number of data, we can get this value, that is a 0.577 multiplied by m. This is purely empirical equation. So, if it is asked that if the degree of thickening is related with the maturity ratio of this equation 0.577 multiplied by m, what is the range of theta value? Range of theta value, the range of theta value will be 0.1158 to 0.6927, because m's range of m is 0.2 to 1.2. If we replace the m by 0.2, we will get 0.1154, and then if we replace this m value with 1.2, we will get 0.6924. So, this is the range. Okay. Now, let us see one numerical here on examining 200 cotton fibers. So, we are experimenting on 200 cotton fibers, 120 fibers are normal fiber, 60 fibers are semi matured fiber, 20 dead fibers are observed. So, 120 normal fiber, 60 semi mature fiber and 20 dead fiber. So, what is the maturity ratio? What we have to do? We have to first convert this value in percent. We cannot directly take. Students normally make mistake, they use direct value of 120 and 20, then it will give a wrong result. So, this is we have to convert into percentage. So, matured fiber or normal fiber, this is 120. So, if we convert into, and semi mature is 60 and dead fiber is 20. So, if we convert into percentage, so total number of fibers 20. So, this is the equation relationship, and percentage normal fiber and percentage dead fiber we have to calculate. So, percent normal fiber N is 60, percent dead fiber is 10. Then if we use this equation, it will become 0.95, that is the 60 minus 10 divided by 200 is. If we use 120 and 20, then we will get a wrong result. So, this 0.95 is the actual maturity ratio. Okay. And from there, if we know this thing, we can calculate the degree of thickening by earlier formula. Okay. Next is the caustic soda method with option 2, second caustic soda method, classified only into two groups, matured fiber, rod like fiber, and with the which have actually have wall width greater than equal to 1/4 of ribbon width, that is the way, and immature fiber. So, it is a simple method. In industry we normally use this fiber, this is quick method. What we have to weigh? We should know the matured fiber and immature fiber. So, mature fiber, it is a rod like structure with wall width which is more than equal to 1/4 of the ribbon width. Total width, if we know the total width, and with the total width we are not concerned about the measurement of the lumen, here total width and the width of the wall. So, that way if it is more than 1/4 then it is mature, and rest all other fibers we can term it as immature fiber, and percent maturity can be calculated by dividing the number of mature fiber by the total number of fiber. So, this is the maturity percent we can calculate here. So, total number of mature fiber which is having wall thick width more than 1/4 of the total fiber width, ribbon width, divided by total number of fibers. Next is that it is a double compression method. In double compression method it is a this principle is used in Searle FMT, fiber fineness maturity tester. Okay. In that case the same fineness instrument is used, where we measure the fiber fineness by air flow method. Okay. But in normal fineness method what we do, we measure the air flow by single compression. We compress the fiber mass in a particular volume. Okay. So, in normal measurement, so as we have discussed earlier, so we take the fiber and we compress it up to a certain volume, okay, and then we measure the air flow rate. Okay. And in this method, for same fiber, same quantity of fiber, we compress half of the volume up to this is one volume, and this is same fiber with the half of the volume. Okay. So, it is a double, it is a compactness has become double. But here what happens, here the fiber surface area, specific surface area is same, both the fiber because quantity of fiber is same, specific surface area will be same, but due to the maturity of the fiber, this fiber ultimately will give the different flow rate. Okay. So, double compression principle is there. It is virtually a parameter of constant flow type. Okay. So, constant flow type measurement that we have seen in the fiber fineness measurement, 4 gram of properly opened and mixed cotton sample is packed into a constant volume, as we have done in fiber fineness tester. Then constant air flow is passed through the sample and pressure drop is recorded. So, we measure the constant air flow, okay, constant air and pressure drop is recorded. Now, the specimen is then compressed to a packing density equal to twice the first one. That means, we are compressing it to a half of the volume, okay, and the test at the controlled flow rate, the same flow rate, and the pressure drop is recorded again. So, we record the pressure drop again, okay, and using the maturity ratio and percent mature fiber are calculated from the regression equation, because it is in this instrument regression equation are already formed. Okay. From there we can calculate the maturity ratio. If we know the pressure drop for a particular flow rate at two different compression level, and using the regression equation we can calculate the maturity ratio and percent mature fiber. The regression equations have been determined from large number of samples. It has already been formed, regression equation, only thing it gives the pressure drop value, and automatically it will convert it to maturity ratio and percent mature fiber. This process is known as double compression technique. Okay. Third is that caustic air method. caustic air method, it's a combination of caustic soda method plus air flow method. Now, as we know that the fiber when absorb caustic soda it gets swelled, and swelling depends on the degree of maturity. If the maturity is a dead fibers are there, this fiber will not get swelled. Okay. Now, also the swelling means the diameter increases. If the diameter increases, the air flow rate will increase. So, the rate of change in air flow after caustic soda treatment will give idea about the immature fiber. Suppose consider there are the fibers are 100% dead fibers, 100% dead fiber. So, what we are doing? We are actually measuring the airflow before caustic soda treatment. We are getting one particular flow rate. So, F1, and after treatment of dead fiber, that means it will not swell. So, the specific surface area will almost remain same. So, that it will give almost same value. So, let us see. So, these are the dead fibers, and the dry fiber, through dry fiber we are flowing the air, okay, and it is giving one flow rate F1, it is a dry fiber. And another case, after caustic soda treatment, it has not been swollen. So, it will give another air flow which will be close to F1, almost equal or close to a little bit higher. So, this ratio, so F1 by F1, ideally I am telling this will become, here it is 1 flow rate, but on the other hand a normal fibers, mature fiber, okay, and after it is getting swollen, it will have different air flow rate, because it is actually it increases the diameter, okay, increases the diameter. So, it is becoming larger. So, in that case the fiber, the air flow through the fiber will be much higher. So, that as it is the diameter is more. So, air flow will be higher for treated fiber than the dry fiber. So, the ratio will give idea about the degree of maturity. So, it is the caustic air method is as per ASTM D2480-82 standard, utilizes standard air flow instrument, but tests are made on normal cotton, on cotton sample that have been swollen on caustic soda. Okay. So, normal cotton means without treatment, another is by treating with the caustic soda, and the ratio of air flow rate is taken as the estimate of maturity index. Okay. So, for 100% dead fiber, maturity index will be 1, there is no change, but for normal fiber the maturity index will be very high, because its total, its diameter has changed. So, air flow rate has increased, the ratio of air flow will be changed. This method is known as caustic air method, it is as per ASTM standard. Next is used in HVI method, high volume instrument. In high volume instrument, normally it is a basically that it is a micronear value is measured. Okay. Micronear is an indicator of cell wall thickening and air perimeter. So, micronear it is in HBI we use normal air flow method directly measure the micronear. Now, AFIS technique. So, HBI and AFIS we will discuss separately in next class, but here let us see the how maturity is measured in AFIS. AFIS works in the photoelectric principle. It actually captures the total image of the fiber. Now, this is the fiber here and it is a lumen here and all this. Now, this one is a perimeter and here it measures the degree of thickening. Now, what is degree of thickening? Degree of thickening is the ratio of actual cross section to the cross section of circle of same perimeter. Okay. Now, for that as we have seen we need to measure first is cross sectional area of this fiber and then perimeter. So, in AFIS here the principle is that multiple scattering angle determines the shape. So, at multiple scattering from different direction it gives the actual shape of the fiber. So, when fiber flows through the in air it captures the image by multiple scattering and it gives the actual shape of the fiber cross sectional shape, and from there we can calculate the area cross sectional area of this. So, this from this perimeter and also we can measure the length of the perimeter, because here it captures individual data at each and every point of the perimeter. From there it calculates the shape and actual area. So, accurate measurement can be made for single fiber, perimeter and area. So, if we capture the data, so we can calculate accurately the perimeter and area. From perimeter and area as we have seen earlier, we can calculate the degree of thickening. So, maturity here then is expressed by the following term. So, one can ask question. So, in AFIS if we get the perimeter and area, how can we express the maturity degree of maturity? Here we can express the degree of maturity by the term degree of thickening, which is 4 pi a by perimeter square, that we have seen. Okay. And percent immature percent fiber content, okay, immature fiber content we can also measure, that is percent of fiber with less than 0.25 circularity. So, as we have data we can calculate the individual data of the perimeter, we can calculate the circularity also. So, less than 0.25 circularity is called the immature fiber. Okay. So, we can calculate the percent of fiber. Okay. And maturity ratio, it is the ratio of number of fibers with 0.5 or more circularity to the fibers of 0.25, okay, to a number of fibers with a 0.25 or less circularity. So, that way if we can calculate the circularity, then we can calculate the maturity ratio also, but this maturity ratio is entirely different from maturity ratio which we have seen, which we have calculated earlier. Okay. These are total entirely different. Here they have in AFIS they have expressed maturity ratio with by this by the way of circularity. Okay. Because in AFIS the advantage is that they can in that instrument it the actual shape can be predicted. Okay. And by image processing technique also one can calculate the maturity. Here it is a individual fiber, here image can be grabbed and the shape of the fiber can be captured. Okay. And if we know the shape of the fiber, so the cross sectional image of mature fiber and the immature fiber, okay, cotton fiber are obtained, and when the actual shape of the fiber can be obtained, in that case we can calculate the degree of thickening. Okay. Degree of cell wall thickening is calculated using. So, it is very clear, we will see the degree of cell wall thickening we can calculate, we can measure where we use the photographic principle, that means where we use the light principle, where we can measure the cross sectional shape of the fiber. So, from there if someone say that okay, if we measure the cross section of fiber, which parameter we can measure. So, that is the degree of cell wall thickening. Okay. Now, another question can be by measuring diameter of fiber or by measuring the cell wall thickness, can we measure the degree of thickening? It is not. Here we have to measure the, because degree of thickening and degree of cell wall thickness people get confused. Okay. From there we cannot measure, but if we can measure the perimeter and actual area, then only we can measure the degree of thickening. Okay. And the last technique is that NIR technique, it can be measured based on the absorbance spectra with respect to wavelength of different cotton sample. So, this is the absorbance spectra and wavelength. From there one can actually predict using some specific equation, one can predict the maturity of cotton. Okay. And this is all about the maturity of cotton. Thank you.